We saw that in order to get to be able to make predictions for complex data, we need to use some nonlinear activation function. Some examples of commonly used activation functions in neural networks are given on this slide here. First, we're going to look at the sigmoid function. So the sigmoid function is this blue line here in this graph, and this is what it does. So in this function, if we give it this sum that we compute from the product of each neuron from the previous layer and the value that connects that neuron and the weight of the connection that connects that neuron to the current neuron that we're in the current layer, and the sigmoid function returns 1 over 1 plus e to the power of minus this value that we get from the previous neuron, or previous neurons, I'm sorry. Right, exactly, and we can see the gradient of each of the functions as well. So this is the derivative, what the derivative of this function looks like as well. Then another commonly used activation function is the hyperbolic tangent. That's this blue line here, and we can see its gradient here. So this function is given down here. We can see it's maybe a bit more complex. However, it looks similar to the sigmoid function. And another commonly used activation function is given here. This is the rectified linear unit, which returns either this value that I just mentioned. So so the sum of the product of the neuron and the weight that connects it to the neuron in the current layer for all neurons in the previous layer that are connected to the neuron in the current layer. So it's either that value or 0, whichever is larger. So if this value is positive, then we get that value. If the value is negative, then we get 0. And we can see it's so what this function looks like here and what its gradient looks like down here. There are other commonly used activation functions. One of them is the softmax function, and there are many others that we can use in our neural networks. And all of these have some advantages and disadvantages in terms of how useful they are and how computationally expensive they are. However, it's also important to know that some functions could be more suited to some different problems. So we'll look at more in depth in the sigmoid function. The advantages of the sigmoid function is that the gradient is smooth and therefore we don't get any jumps in the output values. So the output values won't differ too much. Then the output values are bound between 0 and 1. So the output of each neuron is normalized. So unlike, for example, the ReLU function in which the value can go as high as the output that we get from the previous neurons. Here the output value is normalized. So each neuron will have, so there won't be any neurons that output much larger values than, or much smaller values than any others. And we have clear predictions. So if x is above 2 or below -2, so if x is suitably large or low, then the y value, so the output that we get as a signal or the prediction will be very close to 0 or 1, and this will let us make clearer predictions. However, the sigmoid function does have its disadvantages. One of them is the vanishing gradient. So if x is very high or very low, the the prediction almost won't change at all if the value changes slightly. And this causes a vanishing gradient problem. So if x of the input value is very high or very low, then the gradient will be so small that the difference won't be noticeable. And if this happens, then the network can refuse to learn further. So the weights won't change enough to reach an accurate prediction in any reasonable time. Then another disadvantage is that it's not zero-centered, and also one of its biggest disadvantages is that one of the biggest disadvantages of the sigmoid function is that it is computationally expensive.